IP addressing. In this nugget, we'll be talking about IP addressing, and we'll start off with just assigning addresses. How in the world do you do that? And of course, that's probably a little bit of a basic idea that you're already somewhat familiar with, but we'll quickly review that, as well as IP4 addressing and what addresses really consists of, and then the bits that are there and so forth. We're not really going to address, by the way, custom subnet masks in any detail. It doesn't seem as if Microsoft is emphasizing that as much as they used to. And I guess there's an assumption that you do know something about that already at this stage. Also, we'll take a look at IP version 4 usage, and in particular, private IP addresses and what ranges are available for that. And then we'll take a look at IP version 6 addressing, what IT bits look like, and it's going to use hexadecimal numbers. We'll take a look at how to interpret what you see there when you're looking at IP addresses there. And then we'll take a look at IP version 6 types of addresses as well. There's a number of different types there that have different purposes. Link local and global and several other types, Anycast, some things like that. And then we'll take a look at how to make the two work together. TCP/IP version 4 and version 6, how do you make them work together, especially if you're trying to communicate with from one version to the other. Alright, now as an enterprise administrator, you're probably already very familiar with a lot of IP version 4 concepts and how to do certain things, but we'll kind of do some quick review here so that we can make sure that we're up to speed for what the exam might expect of us. First of all, just remember that when it comes to assigning addresses, you can do so manually, of course, and you know how to do that, but I'm just going to quickly go down here to the Network and Sharing Center, and as I go into this, we can see that we can manage the network connections, and then I can right-click on a connection and choose Properties. And as an administrator here, then, I can double-click on the IP version 4 and change that to whatever I want it to be. So that's pretty much the main idea there of how we can configure IP addressing. Of course, you can also use the net shell command, that's NETSH, to also add an IP address to a given interface. So, of course, you can assign IP addresses manually. You and I both know, however, that that's extremely cumbersome if you have any number of computers on the network, any number of hosts. If you're just in a small lab where you have a handful of computers that you want to have with static addresses, that you want to always know what the addresses are and you don't want them to ever change, sure, you could do that easily. Also, you'll want to manually configure addresses for any servers, because you generally do not want servers to change their IP address. You don't want the Exchange server to suddenly be at a different IP address because it got a different address from a DHCP server, and then for any clients that had been pointing to it by IP address to get lost and not be able to find that server. And of course, I understand that a lot of servers nowadays are also located by name anyway, and so that would hopefully update. But then you'd have also a window of time where potentially the address would get updated in DHCP, but DNS had not yet been updated, so you'd still have some outages there. So manually, we only do that when we have to on generic hosts, but on servers we generally always will do that in most cases. And then we could also use DHCP. This is going to be more for your clients. So again, manual for your servers mostly. Okay, and then for your clients, you normally want to use DHCP. And the reason for that is because it's not practical to go around to hundreds or even thousands of host computers and manually enter in a static IP address. And then you'd have to manually enter in usually other information as well. And then what would happen if you had just entered in 1,000 hosts manually? Wow, there goes your weekend. You just entered all that in, and then someone comes up with a bright idea saying, hey, you know what? We need to change our subnet. We need to change our scope. So now you got to go back to all those clients and change them all. So even the slightest of change will require that you put hands on a great many computers. Not really a very good idea. That's why we use the Dynamic Host Configuration Protocol, which, as you know, uses something called the Discovery, Offer, Request, and Acknowledgement functions. That's DORA, or Discovery, Offer, Request, and Acknowledgement. This is where a client will issue a discovery broadcast looking for a DHCP server. The DHCP server will hear that request and offer an address. The client will say, yeah, I'd like to request the address you offered, and then the server will acknowledge that you do indeed have that address. So the DORA process goes on. And then, of course, your clients will have a DHCP address along with any other configuration. The most common other configurations they'll have will be 3 items. Number 1, the default gateway that you want the clients to use. Number 2, potentially a WINS server, not quite as often as we used to, but you may still have applications that depend on WINS and NetBIOS name resolution. And despite the fact that we have DNS servers in Windows Server 2008 that can resolve a flat name, it's not really still NetBIOS name resolution. So for NetBIOS, and this is important to know, for NetBIOS name resolution, you must still have a WINS server. Okay? All right, so those are the kind of things you'll get. And then finally, the third thing that you would get out of a DHCP address is going to be the DNS server or servers that it needs to get. So you'll get its IP address, you'll get the default gateway, you'll get the WINS if necessary. Hopefully it's not. And then lastly, you'd get also a DNS server. And there's other custom things you can configure in this, but those are the most common items, of course. And then you'll also have some redundancy involved in this. So, for example, here if I've got a router, and on one side of the router, I've got one DHCP server, and on the other side of the router, I've got another DHCP server. We can use the 80/20 redundancy. So on this subnet, let's say that I'm 10.10.9.x, and on this subnet, it doesn't look like a 9. Let me change that. 9. That looks like a 4. But anyway, let me fix that. Okay, 9.x, and over here I've got 10.10.8.x. Boy, I'm having a hard time with my penmanship today. Then what we could do here is to set up a DHCP scope on this server that serves these clients, any other hosts that are on this particular subnet, to give them a 10.10.9.x address range. And if we give them 80% of that, I can't talk and think of math at the same time. So if we make that a Class C address range, that would be 254 addresses that we could use. Not quite 255 because that would be a broadcast, so it would be 254 addresses. And let's multiply that times 0.8. So that's 80% would be 203. Let's round that down to 200. So it would be 10.10.9.1 through 200. Okay, would be the kind of address we could use for our 80% over here. Okay, that's our 80%. Then on this DHCP server over here, we would want it to be able to fill in just in case this one went down or it was out for maintenance or something like that. Okay, or maybe we took it out, I don't know, to get waxed and detailed or something. So if it was gone, then we would need this DHCP server over here to fill in the gap, and it would have a range of 10.10.9.201 through 254. Okay, and that would be the 20% range for this subnet. Now, the way that the clients over here will be able to get an IP address from this DHCP server depends on a couple of things. Number one, Microsoft's old answer always used to be you need to install the DHCP relay agent on some other host over on this network. And then when it hears the DORA and when it hears the D trying to discover a DHCP server, it would then say, hey, you don't have a DHCP server here, but I hear your request, so I'm going to forward your request across the router over to this server, and it would have this specific IP address configured in the DHCP relay agent. The thing is, you can still use that if you want to, but a lot of routers nowadays will be able to fulfill this function for you, and so you just simply configure that on your router instead of installing a DHCP relay agent on a Microsoft server. And then, of course, we would do the reverse over here as well for our 10.10.10.8 address over here. We'd give 80% of the addresses over here, and then 20% over here in case this DHCP server went down. And then, of course, if there is no DHCP server available, then with IP version 4, if it's not able to get an offer when it does this discovery process, if it never receives an offer, then the client will self-assign an address in the 169.254.x.x range. And this would be an address that would be used, but it's only useful for the local subnet. So if there are any other clients that were also unable to get an automatic address, they would also get an address in this range, and those two computers could then communicate with one another, but they would not be able to communicate with any other servers that had static addresses, say on this subnet over here, that had static addresses that were still in this range, because we're in a totally different range right now. So APIPA addresses are really of only limited usefulness. You can only communicate with other APIPA hosts. The other thing is APIPA addresses are not routable, so I would never be able to go from an APIPA address here to this other network or out to the internet or anywhere else. Only works on my own local subnet. And then the other good thing about a PIPA addresses is it's an easy troubleshooting item. I mean, if you have a host that you can't seem to understand why they can't get on the internet or why they can't contact the Exchange server, just do an IP config real quick. And if you look at an IP config, and if that IP address that they have is not in your normal range, but instead it's a 169.254 address, you know right away something's not right with DHCP. So it could be the network adapter on the host that you're working on. Maybe it's going bad, or maybe it just got unplugged. Somebody was doing some cleaning behind the computer, accidentally unplugged the network cable or something like that. Well, that kind of thing could go on, or the DHCP server might really just be down. But this is an easy troubleshooting item when you see that address range. Now, for just about any Microsoft exam, oops, I just zoomed in. I don't know how I did that. Anyway, so for just about any Microsoft exam, let me get my pictures back over here, you will need to know about a lot of those things that I just mentioned here, okay, and especially for the current exam that we're looking at. Okay, you'll definitely need to know the 80-20 redundancy. I think I know what I need to do here. Go back to my pen. The 80-20 redundancy item. You'll definitely need to know about the DHCP relay agent, because Microsoft seems to still have that as a favorite topic at times, even though you might not really need it in modern networks. And definitely also this PIPA address range. Now, also as a quick review, let's take a look at what makes up an IP version 4 address. Remember, it's really just a 32-bit address space, and your computer is really going to be seeing a continuous string of 32 ones or zeros. That's all your computer sees. But for us, us weak-minded humans, we need to see 4 octets just to make this a little bit easier to read. You get cross-eyed looking at just a bunch of ones and zeros. So this is also a decimal conversion instead of looking at it in binary like your computer would see it. So if we had a 192.254.2.1, it would look like this in binary. And again, you don't even have the dots here in the computer language that would see it. It would just see it as a continuous string of ones and zeros, but we put the dots in here to make it easier to read, so that we can equivocate that this range in here, in front of this dot, is what a 192 would look like. And you know how this works in binary. This first bit position is not actually a literal 0, and this 1 is not a literal 1 in the sense of how he normally thinks of ones and zeros. Here, it really just represents whether or not something's turned on or off. Since this bit position is turned off, we don't count it. Since this bit position and this position are turned on, we count them. And what we do is we have to count what values are in those bit positions. In the bit positions, this first bit position is a 1, this one's a 2, and then you double it as you go along. So this is 1, 2, 4, 8, 16, what's next? 32, 64, and 128. So for this, we have our 2-bit positions turned on here at the end. That's a 128. Remember I said that? And that one was a 64. So you simply add the two together, and what do you come up with? Voila, 192. That's how I know that's a 192. Now, of course, you can always use the calculator if you get a little cross-eyed. One thing that's kind of cool about this, by the way, as well, is Microsoft did not always give us the calculator in exams, but it seems as if they're giving these to us now. So if you really need a little bit of help with this, you can do it. Okay, so I say 192. Boy, I just can't seem to think of what that is in binary. Let's see, that would be... Oh, that's right. 1, 1, and then followed by 6 zeros. So, kind of handy that you can at least have that. Of course, this one's a 254. If they were all turned on, that'd be a 255. So that one was easy because I knew I could just make this last one a 0. That'd be a 254. This is a 2. Remember, there's a 1 in this position, but it's turned off. There's a 1 in this position that's turned on. That's our position of 2. So that's a 2. And then a 1, which would be, in this case, all zeros and then a 1. So that's what your binary bit positions look like. And this may be something that you've been working with for years. You're accustomed to them. You like them. You don't ever want to change. Well, guess what? Get used to disappointment, because you know what's coming, don't you? Yep. IP version 6. That's definitely going to make you cross-eyed, folks. But in the meantime, let's talk a little bit more about IP version 4. You know that it's good for about 4 billion addresses, which, of course, nobody ever thought we'd run out of. But they were poorly distributed. Not anybody's fault. It's just no one would have ever known how the Internet exploded and things. I think I recently heard from my friend Jeremy Chowra, who does all of our CBT Nuggets for Cisco topics, or a lot of them anyway. I think I heard him say that Asia got a single Class C address range. Can you believe that? A single Class C address range. Whereas other universities, like I think the University of Utah, got 4 Class B addresses for themselves. And guess what? They're not even using the 4 Class B addresses. They're using something else. They're just kind of sitting on those. And a lot of universities that caught on early to the internet kind of just parked on a whole clump of addresses, but they don't want to give them up because they know they're kind of getting scarce. There's probably a black market in IP addresses somewhere. Let's also take a look at how IP4 addresses are used. And one of the key things to look at here is the private addresses. This is very important because most corporations will use private addresses for their internal clients. Some exceptions there would be a lot of universities and government systems will still use public addresses for their internal clients. And that's a little bit less secure. I mean, there's certainly ways to attack a host in a kind of roundabout way, even if they're using private addresses. However, it's a little bit of a speed bump, so it's a little bit more secure to use a private address to obscure your addresses inside of your internal network. And the reason why it adds a little bit of security is because these private addresses in the ranges that we have here are not addressable from the internet, because internet routers do not route those addresses. So these addresses would work fine within my own corporation. I could check my email from the Exchange server. I could, log on using the domain controller, do all of the stuff that I need to in my own corporate network. And then in order to access the internet, since these don't route, I'd have to use a NAT server, a network address translation server, such as ISA servers or Cisco devices of some kind or whatever. Lots of network equipment would do this for us. But our private addresses here that are usable only internally would be in the 10.x.x.x range, or sometimes you'll see that expressed as 10.0.0.0. And let me put this out to the side here, 10.0.0.0. And then you'll also see the slash notation here of 24 or whatever the subnet mask is going to be used. And in this case, since it's a Class A by default, that would be an 8. Okay, and that means that for my first octet with all the bits turned on, if we added up all of the representative numbers, that would be a 255. Okay, so it would be 255.0.0.0. Okay, that would be the same as, expressing it that way, would be the same as doing a /8 here. Okay, because you turned on the first 8 bits in the first octet, they all added up to 255, and that's it. This is also, again, a Class A, by default. You can change that if you want to. I'll also talk about it shortly. But by default, that's what you'll have. And that's good for like 16,777,216 addresses. So quite a few addresses that you can use there. Then we have a Class B right here. This can also be addressed or expressed as 172.32, for example, 0.0. So I'll do that, 172.32.0.0 /. And then since it's a Class B by default, we would be using a larger subnet mask, Class B, and that would be a /16, which means that all 16 of the leftmost bits are turned on. That would be the first 2 octets are turned on. So that would be a, let's see here, we'd have a 255.255.5.0.0. Okay, so that's what your normal classful subnet mask would be. Then we would have a Class C address range, and by the way, this one goes from .16 to .32, anything in those ranges. This one is a Class C, and with this one, we can have 192.168. Any number that we want here, anything from 1 on up, for example, then that would be a Class C address range, and we'll normally express that as a 192.160. Let's start that over again. 192.168.0.0, and then a / 24. Okay, which would give us a 255.255.255.0. Okay, and that's just the classful subnet mask that we would normally use there for Class A, Class B, and Class C down here. This is good for 254 addresses, or 255 if you count the broadcast. This Class B is good for 65,536. And then again, the Class A is good for 16 million or so. Now, you don't have to memorize those numbers in particular, but you do want to understand that the Class A is an enormous number. Class B is still large. Class C is a little bit more manageable. Plus, on most Ethernet networks, you don't want to put too many hosts on one anyway, so it's going to be a little bit more manageable that way. The other thing is, you could use something called CIDR, which is classless interdomain routing, also known as custom subnetting, depending on how you divide things up. So, for example, up here, I've got a Class A address, But I'm not really using that. In fact, I'm using that in my own network. Let's go to a command prompt, and I'll do an ipconfig /all. And we can see that from my own IP address here, I got a 10.10.10.70, but look at this. I'm using a Class C address. So because of that, it's really only got 254 addresses that are possible on it, and I kind of trimmed it down and scoped it out to my own purposes. I don't really need 16 million hosts here. And I like to use 10 dot addresses because there's less typing to do, and I'm just lazy enough so that one extra character that I would have to type is just too much work. So I like the 10 dots for my own purposes, but you can just use whatever you want. A lot of our home networking items, like Linksys routers that people use for their wireless networks and stuff, normally those are going to be configured in the 192.168. And I think it's .1 or .2 or .100 is a lot of the vendors are using those ranges. Okay, but anyway, again, you can divide that up however you want to as well. Maybe I wanted to not just use a strictly Class C range in here. Maybe I wanted to go 255.255.172 or something like that. Well, you can do that as well, and what you'll do is you'll just borrow some of the network bits and you'll give them to the host bits. Or if you want to narrow down, give yourselves fewer hosts but more networks, then I would borrow from the host side and give myself more network bits. And again, a lot of this is probably review for those of you, old hacks that are already accustomed to doing a lot of IP4 addressing. And then this is probably not an exam issue, but just as an FYI, there's also supernetting. So if I had something like 192.168.1.x and 192.168.2.x and 192.168.3.x, you can supernet those to kind of make them all one aggregate range of addresses. As long as they're contiguous, I can do that, and that's something called supernetting. And that's useful if I don't really have a bigger address range. I just got a whole bunch of really tiny carved up little address ranges, maybe even really customized address ranges, which only give me, a few hosts per subnet. Well, I might want to put all of those together and kind of combine them together. That's what I would use subnetting or supernetting for. All right, now is where we get into really big numbers with IP version 6 addressing. Now, I'm not going to go into all of the rationale for why we need IP version 6. You probably already know the main reason, and that is that we have exhaustion of the IP version 4 address range. There's just no more addresses left. With IP version 6, it's nearly inconceivable that we could ever run out of addresses. Now, they said that for IP version 4, I know, but really, this is just an astronomical number now. Instead of being a 32-bit address, it's a 128-bit address. And this is an exponentially larger number than a 32-bit address, so that gives us about 4 billion numbers. Also, this is going to give us 8 groups of about 4 hex characters. Okay, 8 groups of 4 hex characters. Now, at first, when I thought of IP version 6 addressing, I thought, okay, IP version 4 was something dot something dot something dot something, and that was IP version 4. So IP version 6 must be just 2 more, right? No, it's nothing like that at all. And this is a huge number of addresses, and it's a great deal larger. First of all, with 8 groups of 4 hex characters, the hex characters themselves each represent 4 bits. So, in an IP, let me just look at an example here. In something like this, these 4 numbers here, these 4 positions in an IP version 6 address, this actually represents a total of 4 bit positions. Okay, this next one here also represents 4 bit positions. 4 bit positions. 4 bit positions. Okay, I'm going to show you a table as well that helps you kind of translate some of this as we go. But so you can see there that the way that we've compacted this, and we don't have to use all 128 bits from left to right, which would be even more difficult to read than this already is by using hex. We can kind of compress the way that looks. Okay. Also, the valid characters that you'll have in hex are 0 through 9 and A through F. And so those are the numbers that you're going to be able to see. And to make that easy, I've got a conversion chart for us here that I've put together. You can download this from nuggetlab.com. And I also recommend that if you want to calculate any kind of these numbers, go to easycalculation.com, and there's a hex converter there that you can also look at, which of course is really identical to this, simply because there's no other way to interpret all of this. But for example, if I had this number right here, that would be in binary. Remember, our first bit position there is a 1, but it's not being used. So then we have our 2 that's being used, and a 4. 2 plus 4 equals 6. So in hex, that's 6, and in decimal, that's 6. This doesn't really get interesting, though, until you get into anything past 9. Now, even though that's a 9, that's actually our 10th number because we start with a 0. Okay, so that's actually our 10th number. We get into our numbers down here, though. Now, when I get to the number 10 in decimal, in binary, that would be expressed like we see right here. So it would be a 2 plus an 8, right? That equals 10. But in hex, that would be represented by an A, okay? Because it can't use 2 digits to represent a 10 the same way decimal does. It has to be a single position that represents the number 10. Okay, likewise with B, the B would be the number 11. And that would be because we have a 10, there's a 8 plus a 2 plus a 1, that's 11. And that would be represented by a B, and so on, so forth down the line until you get to F, which means that all bit positions in the binary are turned on. So, that's why your IP version 6 numbers look a little bit different because they're using hex numbering instead. Now, how many numbers is this good for? It's good for whatever that is. If you can name, in 5 seconds or less what number that is, whether it's a bazillion or whatever it is, well, good for you. I give out, let's see, there's hundreds, thousands, millions, billions, trillions, quadrillions, I don't know, septillions is in here somewhere. And after that, I kind of pretty much give out. I don't know. I'm too dumb to really know what the rest of that is, quite honestly. But it's some big old gigantic number. And a lot of people have tried to express that in terms that, mere humans can understand. Someone once said that with this kind of a number, each human on the earth could have 4 billion addresses. So it's as if each human on the earth had their own IP version 4 address range all to themselves. So that's the kind of number it is. It's just a lot of different ways have been trying to express that. It's really beyond comprehension, though. Now, a couple of other rules with our IP version 6 addressing, though. That is, number 1, we can eliminate consecutive zeros with a colon. You can only use that once in the address, however. If there's more than one section that has consecutive zeros, you're out of luck. You can only use that one time. Also, you can drop leading zeros. Now, as an example of that, I'm going to show you how that can express right here. Here in this address that I had up at the top, you can express that this way. FD00, that's going to be the same. Okay, this is going to be the same as well. Then here we have leading zeros. Well, we can drop those and just enter in a 6. Okay. Then we have 0, 0, 0, a whole bunch of zeros there, whole bunch of zeros there, whole bunch of zeros there. They're all consecutive in the same octet. I shouldn't say octet because that's a group. Okay, that's what we had in the old IP version 4. So since these are all zeros, we can compress those down into just this colon. All right, and then this would be the same, and then of course this would be the same on the end here as well. So you can see that we can compress the way we express that IP address by using the colon and by eliminating any leading zeros. Now let's take a look at the IP version 6 types of addresses that you're likely to encounter. There's actually a number of different kinds, but I think in terms of exam objectives and what you're likely to actually run into and need to use, you'll be seeing some of these that we'll look at here in these next few whiteboards. And the first one there would be a link local. Now this is similar to the APIPA address. Those are the automatic private IP addresses that are in the 169.254 address range, and normally when you see that in an IP version 4 network, that's a bad thing. That means the DHCP server's down, and I've got an APIPA address. Oh no, what am I going to do? Well, with an IP version 6, the equivalent is a link local, but you always get that. Even if you have a functioning DHCP server, you're still going to have a link local address, and your hosts on the same network are going to be able to communicate with one another on that link local address, and that's okay. Because also, another part of this is that with IP version 6, you can have multiple addresses bound to a single adapter, whereas with IP version 4, normally you're going to have a single one, at least by default. So you'll have your link local, plus you'll have another, like real address that I'll talk to you about here after a bit. Then you'll see this visually can be identified as an FE80, but we usually just call it FE8. And this represents the first 10 bits of the address space, because the F, remember, each one of these bit positions is going to represent 4 bits. Okay, so the F would be 1, 2, 3, 4. All the bits are turned on. Okay, if we go back to our conversion item here, an F, All 4 are turned on. All right. And then an E, what would an E be? Well, an E would be 1110. So that would be like this. Our next bit position would be 1110. And then our 8, what would that be? Well, that would be a 10000. Okay. So that would be a 10000. Well, what we have here in reality is too many zeros. I put too many on there. Okay, so there's 4 plus 4 plus 4. Okay, so those are my first bit positions. Okay, we really only use the first 10 in this idea though. So there's my first 4 there. There's my 4, 5, 6, 7, 8. Okay, and then this is 9, and then 10 right there. Okay, so my first bit positions are represented by this FE80. Okay, after these first 8-bit positions, then we have 0, 0 plus a whole bunch of other zeros. And in total, these 2 zeros plus the remaining zeros are all going to be 54 zeros. All this direction, okay? 54 more zeros. And then we'll have 64 bits on the end, which are going to be represented by our physical MAC address, okay, or machine address, as they're also known. And interjected into that MAC address, we're going to stuff in this. I don't know why the powers that be decided to stick this right in the middle, but they do. So you'll have a part of your MAC address, your first half of your MAC address, then you'll interject FFFE, and then you'll have the remainder of your MAC address. And you don't interject this yourself. I mean, it happens automatically, but this is what it might look like. So you'll have the first part of this FE80, something, 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 a whole bunch of zeros there. And then if your MAC address is this, okay, that's one of my MAC addresses, then the equivalent at the last 64 bits would look like this. 0004, okay, there's my 0004, okay, the first part of that. And then 4B right there. And then right here in the middle of it, we interject our FF colon FE. And the reason why I put a colon in there is because, we have 4 hex positions in each one of these groupings. And since I already had 4 here, I put a colon here to put, to split that up. So then I get an FE, and then I resume my MAC address. 18 here, 18 here, EE6C here, EE6C there. So that's what you'll see there with this type of an address. And again, remember, you always get a link local address even if you're using DHCP. It's just that you'll have your DHCP allocated address and your link local. Now you'll also have unique local addresses. This is what they're called currently, right now under the current RFC. And RFC is request for comments, which was where all of these standards are defined and all the definitions are defined. Microsoft still calls it, however, site local. That's kind of the old term, but Microsoft is still using it in most of the documentation that I've found for them. Now, this is very similar to a private IP address. Remember we looked earlier at some of the addresses which could be, 10 dot addresses or, 172 dot addresses, those types of things. Well, this is very similar to a private IP address. They're not actually necessary. You don't have to have these. Okay, it's just that it's kind of a concession for administrators that, boy, we really like our private IP addresses. We want full control of them, and we want to make sure that our DHCP servers are only issuing private IP addresses. Well, in IP version 6, we'd say we only want to issue unique local addresses, or if you want to call it site local, either way. Now, the way that you can identify these is that visually they're going to start off with an FD00 and then a bunch of zeros. So you have colon, colon. And then /8 here, of course, would again identify that the first 2 sets of bit positions, which are this one's 4 and this one's 4, are going to be part of our network side. So those first two positions are going to be the network side of the address. And then a loopback address, this is different than IP version 4 as well. Our loopback address is now simply colon, colon 1. Let's go to a command prompt. Remember with IP version 4, I could ping my loopback address. And why would we do that? For testing purposes, to see if the IP stack was loaded properly. And you'll do that if you have trouble communicating with other hosts, just so that you can see if you actually have a valid IP stack loaded. But, if in IP version 4, I might do ping, and then, 127.0.0.1. Okay? I'm getting replies back so that I know that, at least in terms of the software, it's loaded my IP stack properly. And by the way, here's a quick little item for you. It's not really 127.0.0.1, it's the entire range. The entire Class A range is dedicated just to pinging yourself. Okay, so I can do 255.255.254, and I can still ping myself with that. Okay, so this is a classic example of the wastefulness of the way that the numbers were allocated for the older IP version 4. Nothing we can do about it now, though. But if we wanted to ping using an IP version 6, you'd do a ping : 1. And there it is. Now we're getting replies from that one. And guess what? With IP version 6, it's just one address. That's it, the : 1. And that's all we have. We don't have a wasted range of addresses like we did IP version 4. Now let's also take a look here at the IP version type of address known as the global scope or global addresses, as you may also see it referenced. These are typically where it's going to be used on the internet, or in IP version 6 lingo, the internet version 2. And with this one, we'll have the high-level bits, or the leftmost bits, set to 001. Okay. Now, if you want to fully express that first position in hex, that would actually literally be 0010. And of course, the first position's off, so we don't count it. The second position represents the number 2, and it's turned on. So that's where we get our number 2 right here. Okay, and then the rest of this can actually be anything, but we will often see this just represented as 2000 : to represent a bunch of zeros, and then again identifying the first 3 bit positions as what represents our high-level 3 bits. Then you'll have a global routing prefix here. And let me scan this out here a little bit, or diagram this out just a bit. You'll have here is your global routing prefix, or I'll just abbreviate this: global routing prefix. This is going to be a specific number of bits. Okay, n meaning any number, up to 48 bits. Okay, and then after that, you're going to have the subnet ID. Just like we have subnets in IP version 4. This is going to be a subnet ID that we'll have here. Okay. Now the subnet ID is going to be the remaining bits in the first 64 after the global routing prefix. So let's say that in the global routing prefix we used 5 bits. Okay. And if we have 64 minus 5, that means that that we would be left with 59. If we have n minus the 64 minus the n bits, okay, that we identified over here. So if we use 5 bits here, then we have 64 minus n. That would mean we'd have 59 bit positions here to identify our subnet. And then the remaining 64 bits over here at the end, 64 bits, would all be for interface. Okay, so you'd have 64 bits. That's a huge number on its own. Even in a single subnet. 64 bits for interface IDs. So we definitely have plenty of numbers to work with right here. And this is just identifying what I told you. Remember, the global routing prefix is going to be 48 bits or less. Okay, that's this global routing prefix section. And then the subnet ID is going to be the remaining bits in the first 64 after the global routing prefix. So if we used 5 here, that would be 64 minus 5. That would give us 59. Yeah, 59 would be 59 bits to identify various subnets. And then the interface ID, again, would be the last 64. IP version 6 Internet is primarily going to be using, you'll see this mostly on the Internet, the 2001 number. That's what you're going to usually see, 2001 actually, :/16 to identify the subnets. So again, that's typically what you're going to see out there. Now another kind of an address that we can use here is the Anycast type of address, which will visually look similar to a global address. So it might be 2001 : whatever. So it looks very similar. And then the advantage of this and the feature of it is that it can use many destination hosts with the same address. Now think about it this way. Let's say I've got a host right here, and it's trying to access some various servers, or any one of these various servers, all of which have the same IP address. So it might, there might be a router here, and there might be a router here, and there might be, a router here, and then this router is separated by another network, and then another router, and then another network, and then another router. Maybe this one just has one other router, and at the end of each one of these is the destination host, all with the same IP address. Okay, so this has the same IP address as this one, and it has the same IP address as this one. Well, this host right here, all it knows is that it's trying to send or receive a message, or send a message to, send a massage. Yeah, I'd like a massage right now. Send a message to a host with that IP address. it doesn't even realize that there's actually 3 of them available through various routers and on my networks that I can reach. So what happens is, with Anycast, is it will calculate according to router cost which one of these is cheapest, so to speak, or closest. And it'll find the nearest one based on router cost. So this host would then, of course, probably communicate with this one, unless I had an unusually slow router cost identified here. But if we just, all things being equal, this would be the one it would use. On the other hand, maybe here I've got another host that's trying to communicate with the same IP address. Well, guess what? It's right here connected to the same router, so it's going to go right here. It's not going to communicate with this one. It's going to communicate with this one because it has a very low router cost to make one hop right over here to this guy. So pretty cool thing here with Anycast. And this also, by the way, and I don't really have it in our notes anywhere here, but this helps to mitigate something that we are missing from all of these types of casts. Notice that I haven't talked about broadcasts. Yeah, that's right. In IP version 6, guess what? We finally get to get rid of broadcasts, and there are a number of other built-in functionalities, including things such as Anycast, which will allow us to communicate with a destination host without broadcasting. Now, how do we get from IP version 4 to IP version 6? This is also known as TCP/IP version coexistence. In other words, how do we live with our current IP version 4 services, applications, version 4 network addresses, and how do we also communicate with other networks that might be using IP version 6? Or maybe we're on the bleeding edge and we're on IP version 6, but guess what? Most of the internet right now is still on IP version 4. So how do we communicate with them? Well, there's what we call a transition richness with this, which means that it's going to be a very easy, smooth, and non-pressured transition. It's going to be easy coexistence with both worlds of TCP/IP version 4 and 6. One of the things that can be done with that would be to use something called dual stack routers. Let me just quickly draw a diagram here, and for expediency's sake, I'm making hosts just be squares. And these are on one subnet right here, and maybe I've got a router right here, and then I've got a link out here to IP version 4 internet. IP4. I'll just put IP4 internet, and then we've got a link out here to IP6 internet. Okay, now if this is an IP4 client and this is an IP6 client, how is this going to work? Well, the IP4 client will be able to communicate with an IP4 network because this router right here is a dual stack router. I'll put DS for dual stack router. This means that it communicates both IP version 4 protocol and IP version 6. So it can pretty much, it's bilingual in that sense. So when I try to go to this IP4 location out here, it just takes me right out there. Okay, no problem right there. Likewise, IP version 6. If I have an IP6 client here trying to communicate with IP6 internet or internet 2, again, this router will take me right out there and no big deal. Now, things get a little bit different though when we have an IP4 client trying to communicate with a web server that maybe is transitioned fully to IP version 6. And how is that going to happen? Well, let me change pen colors to make this a little bit easier to see. When I have this IP4 server that wants to communicate with an IP version 6 host, what happens here is it's still going to go through their dual stack router, but it's going to go to the IP4 internet, and it's going to suddenly realize, oops, well, that host isn't here. It's in some other realm. It's in the IP version 6 IP address space. So what happens then is the ISPs are going to have other routers here that are going to be able to do NAT protocol translation. So it's going to say, okay, you're in IP version 4. I see you're coming from IP4. That's what's identified in your headers, but you're trying to access this guy down here in IP version 6. So it's going to come in as IP version 4. It's going to exit the router as IP version 6 because this network address translation protocol, or NAT protocol translation, or NATPT, actually that's what I'm identifying right there, it's going to be able to perform that translation for me to communicate with this IP6 server. And then when it sends it back through, it's going to come back in as IP6, exit this as IP4 to go back to my host. Okay, and it can do that both ways as well. IP6, up through IP4 as well, so it can do it both directions. Now, another way of easing the transition here is to use tunneling. With this, I can communicate from an IP version 6 network to an IP version 4, or 4 to 6, vice versa, of course. Okay, so I can go either way here. Let me go ahead and take a look at another whiteboard to make this a little bit more clear. Here, maybe I've got a router here, and it's connecting me to the internet, like this. And then I've got another router here. And then on the end of that, I have another, subnet here. Okay, so maybe this is IPv4. All right, maybe we're stuck with IPv4 on our network, and then we have a router, and then maybe the entire internet switched over overnight to IP version 6. Surprise! Yeah, we're all now on IP version 6, but we're still stuck on IP version 4. Okay. By the way, this is somewhat true for a lot of Asia and China and Japan. They have made great strides to going to IP version 6, whereas most of the U.S. is still mostly an IP version 4. But in Asia, they kind of have to because they have a smaller address space for IP version 4. So this is a good transition for them to make. But anyway, aside from that, here I'm going to try to access something across the network here over to this side. How am I going to communicate from this IP version 4 network to this IP version 4 network, where maybe there's a web server over here? But how am I going to communicate through IP version 6? Because that's not really a direct translation, so to speak. Well, what we can have is tunneling, and there's a number of ways of making this work through router configurations. This is not something that we directly configure on Windows hosts, but it's useful to know that it's available. You can communicate using a tunnel here, and I'm not very good at drawing 3D here, but something like that. So now we can take our IP version 4, and if I change colors, it'll be a little bit more visible maybe. And I can communicate through my router, and then when I get to this point, the router will do the tunneling for me through this tunnel in IPv6 land over to this IP version 4 network, so I can still communicate with this IP4 server. Likewise, if all this were reversed, maybe the whole internet was still IP version 4, but we were, on the bleeding edge, and we had upgraded everything to IP version 6, then we could still tunnel through the IP version 4 network because of the way the routers are configured and things like that, outside of the Windows world, so to speak, that would still allow this transition to take place. And there's really no loss, and there's not going to be a notable performance decrement by doing this kind of tunneling and so forth. It really should work pretty seamlessly and relatively effortlessly. So, pretty cool way of going there. And then we already talked about the NAT protocol translation in this diagram right here, where it'll just take an IP version 4 message from a source of IP version 4, translate it through the NAT to an IP version 6, and then allow us to communicate with this IP version 6 network. I kind of already addressed that one. Then there's another one here that you should just know about, again, at least in terms of what it does. That's Teredo. And what this is, by the way, what Teredo really means, something like, I think it comes from the word shipworm, and Teredo navalis or something like that is what that is. But the basic idea here is that a shipworm bores through the wood of an old ship, and it ruins the wood and eventually sinks the ship. Well, hopefully we're not going to sink the internet with Teredo, but what this is trying to tell us here by using this name is that it's going to be able to send messages from one network type of IP version 6, for example, as IP version 4 UDP packets, okay? And the reason why it does that is to work around IP version 4 network address translation, because otherwise IP version 6 packets that would try to communicate directly with an IP version 4 NAT infrastructure, there's no equivalent. So it would have no way of making that communication. But Teredo will repackage those as IP version 4 UDP packets to be able to communicate with IP version 4 NAT translators. And that's what Teredo will do for us. Alright, then here I've returned to Server Manager just so that I can quickly show you how you might configure DHCP with IP version 6. And as you start the wizard here, adding this role, the first thing to identify is that as you add DHCP server, it really is going to take you through the IP version 4 section first, which I'm kind of going to be quick with here because you're probably already familiar with IP version 4. I'm going to bind it only to that address because these are VMware addresses. So any discovery broadcasts that occur on .70 will be received and serviced by this DHCP server. Then I can enter in a DHCP, a nuggetlab.com as my parent domain, or some other domain if appropriate, but it's not. Then I can enter in the preferred DNS server address, which is .70, and if I have another one on the network, and I do happen to have another one on the network, I can enter in that one as well. And you can validate both these addresses to confirm that they're live and running DNS servers if you want. Then I'll go ahead and click on Next. I don't really use Win, so that's not necessary. Otherwise, I could enter in addresses there. And then I can add in the scope, and I'll just call this, nlab IPv4 addresses. Okay? And on the starting address, and we'll do the ending address, and the subnet mask. This is not a lot different than what we've done in the past for other DHCP servers in previous versions of Windows, except that this is kind of new. Wired or wireless. Okay, you can choose one of those. I'm going to make this one for a wired network, and I can also activate this scope, although until I authorize the server, it's not going to actually be able to distribute any addresses yet. But I'll go ahead and click on Next now, and then it asks me whether I want to use stateless mode for the server, or enable it or disable it. Now, this one is a little bit counterintuitive. I think the wizard could have been done better here, but let me explain. Here, first of all, the default option there is to enable DHCP version 6 stateless mode for the server. What happens here is I can still configure things such as which DNS server my IP version 6 clients should use. However, their actual IP address is going to be automatically configured based upon router solicitation messages. So the client will send a router solicitation message to my routers. The routers will send back information about what network that client is on, and then they'll be able to automatically configure an address in that same subnet. Okay, so it's kind of cool. It's kind of halfway between DHCP and a PIPA, if you will. And that's what this first option is. But look what happens. As I click on Next, and if you want to take the time to pause here and read, all of this makes it look as if it's actually going to assign an IP address from the DHCP server. It's not. It's not doing that. All it's going to do is it's going to tell it what the DNS IP version 6 address is for the DNS server that I want it to be able to pick up. So, to review that, it might get its IP address automatically configured based upon the router solicitation message. But the router might not be able to tell it what DNS server to use, so I'm going to tell it what server to use right here. It does not pick up an IP address, okay? Although it says it does right there, or it implies it. So, if I did want to disable DHCP stateless mode for this server, then this would mean that it is going to use this DHCP server to get all of its DHCP configuration, its address, its DNS servers, all the rest of it, okay? And what I would do is I would then Next, and then I would finish the wizard, and then I would configure the DHCP mode using the management console in a separate step outside of this wizard. Okay, so I'm going to go ahead and do that for the time being. I'll click on Next here. Then I'm going to authorize it using my existing credentials. And that's just going to be temporary, by the way, because I already have a DHCP server. It's really not a good idea to have two DHCP servers on the same network, because you don't want them to get in that situation where the right hand doesn't know what the left hand's doing, kind of an idea. But then I'll just go ahead and click on Install on this, and when it's finished with this, I'll return and continue recording. Alright, now I've gone ahead and installed DHCP, configured the wizard, finished the wizard, and then I closed and opened Server Manager because otherwise all these options don't appear. So now I need to go ahead and also configure a static IP address. So I'm going to manage network connections here and configure a static IP address for my version 6 address, and I would do that just right here. And then I would just use the following address, and I'm just going to kind of arbitrarily just type in, I don't know, FEC0, colon FFFE colon A, something like that. I don't know. And then I'm going to enter in a subnet prefix length and enter in a default gateway if necessary here as well. I'm just going to leave that for the time being. Then I'm just going to click OK and OK. That's pretty much it. Okay, so I just entered in some static address, and that's important. Anytime you have a server that's going to service clients in IP version 4 or 6, so that you can make sure that that IP address never changes. And then what I would want to do here is I would go into IPv6 and create a new scope. And so I'd right-click to choose new scope, and then go ahead and click on Next. And I just typed in nlab IPv6 scope, and then I'm going to go ahead and enter in the prefix. And I'll just go FEC0. This of course has to be in the same range, so to speak, as the static address that I just typed in, so colon, and then what did I type in? FFFE, I think. Hopefully I get this right. And then there's a preference idea here as well. which we don't need to set for our current purposes. And then I'll go ahead and enter in the start IPv6 address, and let me just go ahead and enter in a range just like this. And again, I'm kind of arbitrarily just making selections here. Then I click on Add, and go ahead and click on Next. And then I can specify how long I want the addresses to be able to last, very similar to what we had done before with IP version 4. And then we just activate the scope. Really, there's not that much else to it. I now have an active IP version 6 scope. In this nugget, we took a look at IP addressing, and we started off by taking a look at just assigning addresses, where you do that in the interface and how that's performed. We also took a look at IP version 4 addressing. We looked at the various types of bit positions that would be there, 32-bit address and how many addresses it's good for and so forth. And then we also looked at how IP version 4 can be used, and in particular, we looked at private IP addressing because that's very, very commonly the most used addresses in an enterprise. Then we took a look at IP version 6 addressing. It's of course a hexadecimal numbering system, but it uses 128-bit addresses, and we took a look at that as well as the types of addresses that you can use. Remember, you have things such as Anycast, you have global, you have link local, those sorts of things that we looked at, as well as taking a look at how to make version 6 and version 4 coexist, and to give yourself a smooth transition there, or transition richness, as we called it. Well, I hope this has been informative for you, and I'd like to thank you for viewing.